Welcome to Curiosity. Let's run a thought experiment. Imagine waking up to find that at exactly 12 UTC, the universal gravitational constant has spontaneously dropped to absolute zero. For humans, the immediate physical sensation would feel identical to the drop on a roller coaster, only it would never end. Anything not physically bolted deep into the planet's bedrock, people, cars, loose soil, furniture, and animals, would instantly stop feeling the downward pull of the Earth. You wouldn't simply float in place. The Earth is currently spinning, and at the equator, the surface moves at roughly 460 meters per second. Gravity provides the centripetal force keeping everything attached to this spinning sphere. Without it, inertia takes over, and every unattached object is flung tangentially eastward into space. 10 seconds later, the catastrophe reaches the atmosphere. Our air is held against the planet entirely by gravity. Without that downward pull, atmospheric pressure drops instantly. Gases expand rapidly into the vacuum of space, suffocating all life within minutes. Gravity acts as the unseen physical anchor of our entire reality, responsible for literally holding the air we breathe against a spinning rock. 5 minutes into this scenario, water, which conforms to the shape of the Earth solely due to gravity, loses its mooring. Driven by the planet's rotation and plummeting atmospheric pressure, the oceans lift off the seafloor in massive continent-sized sheets, flash boiling in the zero-pressure environment. This table details Earth's physical properties. Notice the bottom row displaying the Earth's internal core pressure. The crust floats over a pressurized mantle of semi-liquid rock, compressing around a dense iron core. Without gravity pushing back against those 3.6 million atmospheres of outward pressure, the planet begins to tear itself apart. Magma violently erupts through millions of new fissures, shattering the tectonic plates and exploding the Earth into a cloud of rock and steam. On a cosmic scale, the moon flies off into deep space. The sun, no longer balanced by gravitational collapse, violently blows its outer layers outward. Without gravity serving as the ultimate cosmic compressor, planets, stars, and galaxies instantly dissolve, scattered by their own internal energy. Fortunately, the gravitational constant is stable, but simulating its absence reveals the immense power required to construct the cosmos. It raises a practical question. How did humanity measure and understand a force we cannot even see? In ancient Greece, Aristotle incorrectly believed that heavy objects fell faster than lighter ones because the center of the universe was their natural resting place. That view held until the late 16th century, when Galileo proved through physical experiments that all objects accelerate toward the Earth at the exact same rate, regardless of their mass. A century later, Sir Isaac Newton synthesized this terrestrial physics with celestial mechanics. He realized that the terrestrial force pulling an apple to the dirt was the exact same cosmic force tethering the moon in its orbit around the Earth. This document outlines Newton's law of universal gravitation. The formula shows that every point mass attracts every other point mass, with the force dictated entirely by the size of their masses and the distance between their centers. While Newton successfully proved the universe operates under uniform, predictable mathematical laws, his equations only described the behavior of objects. He still could not explain the actual physical mechanism of gravity. The mechanical explanation arrived in 1915, when Albert Einstein published his general theory of relativity, discarding the idea that gravity is a traditional pulling force. Einstein proposed that gravity is the geometric curvature of space-time itself. Massive objects warp the fabric of space and time around them, and other objects simply follow the straightest possible paths through that warped geometry. Physicist John Archibald Wheeler summarized it best. Matter tells space-time how to curve, and space-time tells matter how to move. Which brings us back to our thought experiment. If gravity turns off, space-time instantly flattens out, losing all geometric curvature. Without those depressions in space, orbiting objects immediately travel in straight lines at a constant velocity. Gravity is not an invisible rope connecting planets. It is the physical, geometric shape of reality itself. Today, general relativity operates exceptionally well on massive cosmic scales. In 2015, facilities like LIGO even made the first direct observation of gravitational waves, actual ripples in spacetime caused by colliding black holes. Yet, despite these macroscopic successes, our understanding remains deeply incomplete. The universe operates under two highly successful frameworks: general relativity for the very large and quantum mechanics for the subatomic. Mathematically, these two frameworks are totally incompatible. When scientists attempt to describe gravity at the quantum level, like at the center of a black hole, the equations produce infinite, nonsensical results. Finding a theory of quantum gravity is currently the greatest unsolved roadblock in modern theoretical physics. It is a profound irony. The specific force responsible for structuring the infinite macroscopic cosmos completely breaks down when applied to the fundamental building blocks of reality. This chart breaks down the composition of the universe, revealing an even larger epistemological gap. When astronomers observe galactic rotations, the visible matter, the stars and gas we can actually see, does not generate enough gravity to hold the galaxies together at their observed speeds. There is an immense amount of invisible mass exerting a gravitational pull, which we term dark matter. Simultaneously, the expansion of the universe is actively accelerating, driven by an opposing cosmic force scientists call dark energy. To solve these mysteries, space-based observatories like the LISA mission are being developed to detect lower-frequency gravitational waves from supermassive black holes. Physicists are also hunting for the hypothetical graviton, a particle that could finally explain how gravity operates at the quantum level. The normal matter we interact with makes up less than 5% of existence. The rest of the universe is dictated by dark matter and dark energy, phenomena we can measure but cannot yet comprehend, leaving gravity as our most familiar, yet deeply unsolved cosmic mystery.